So again, today's lesson and the next lesson is going to be a lot of terminology. We'll be doing a nice fun lab though next class. It'll be a noisy kind of cacophonous shouting lab. If you've ever wanted to shout in your friend's face, you'll enjoy tomorrow's class. In physics, every measured quantity is either a scalar or a vector. Zena over here had me in Physics 11 last year and Physics 12 this year. Scalars and vectors are a little bit important in Physics 11, but they become much more important in Physics 12, yes? And so I'm kind of planting a seed right now. What's a scalar? A scalar is a quantity that has magnitude only. Magnitude, Acacia, is the fancy word for size. Let me give you an example. Mass is a scalar. Now, to help you understand the difference between a vector and a scalar, I'm also now just going to give you the direction of a vector. A vector has both magnitude, size, but it also has some indication of direction. So if I go back to my scalar example for mass, what's the mass? 30 kilograms. That makes sense. What's the mass? 30 kilograms north. Makes no sense. Mass does not even have the concept of direction. It's a scalar. Other examples of scalars. Time is a scalar. That's going to be the big one that we'll be looking at this year. Area is a scalar. Volume is, don't write all these down. Volume is a scalar. Work is a scalar. Energy is a scalar. Why is that important? As Zena knows, there are different rules for doing physics or math with scalars versus vectors. If you take Physics 12, you'll learn vector mathematics. I'll sneak it in a little bit this year, but you'll learn it really in Physics 12. Vectors have both magnitude and direction. Let me give you an example of a vector. Velocity is a vector. 80 kilometers per hour at 30 degrees north of west. You heard the direction there? Acceleration is a vector. Depending on which way you're accelerating, that will determine whether you're speeding up or slowing down. Force is a vector. So I have a little chart here. Anytime I introduce, Fahim, something new to you, a new concept, I'll do three things. Number one, I'll show you the abbrev, the symbol that we're going to use for it. Number two, I'll tell you the units that it's measured in. Third thing, I'll always tell you whether it's a scalar or a vector. And you will need to memorize whether a new concept is a scalar or a vector. But again, I don't think you'll need to make flashcards. I will flog it to death. Generally, I think you found I just repeated it so often you could remember what was a scalar and what was a vector. Yes? Okay, good. So here's a little chart. I'm just going to give you some examples. I already gave you a scalar, time. And our symbol for time is going to be a lowercase t, not an uppercase t. That's something else. A vector, acceleration, our symbol for acceleration is going to be a lowercase a, except we have a symbol to show something is a vector. To show something is a vector, we draw an arrow over it. Although over the years, look up everybody, instead of doing the complete arrowhead like that, we've gotten lazy and we just do half the arrowhead like that. And that's meant to indicate this is a vector, it has direction. Now, why is that? We don't have enough English letters. We're going to have to reuse some of them for scalar concepts and some of them for vector concepts. And Carrot, you'll be able to tell the difference if it's got a vector symbol. In fact, the next one. Oh, sorry, not velocity. Speed, comma, lowercase v, no vector symbol, and velocity, comma, v with a vector symbol. If I was a good teacher, I'd have a dumb way for you to remember that velocity is a vector. If I was a good teacher, I'm sure I could come up with some way, Brett, for you to remember that velocity is a vector. Oh, and if I was a really clever teacher, Eric, I'd have a way for you to remember that speed is a scalar. I'm sure if I was a really good teacher, I'd come up with some way for you to remember that speed is a scalar. I can't think of anything, so you'll have to come up with something on your own. Sorry, I'm a terrible teacher. Okay. Distance is a scalar. Displacement is a vector. We're going to use the same letter for both of them, a D. One has a vector on it, vector symbol, that little half arrow. One does not. Unfortunately, Mallory, I don't have a good way for you to remember that distance is a scalar and displacement is a vector. That one, you will have to come up with something on your own. And if you come up with something really good, let me know. I will use it for the remainder of my teaching career and give you credit. I've just brute forced it through sheer repetition. I know that distance is this, because they both begin with a D. In fact, they both begin with a DI. In fact, they both begin with a DIS. I haven't come up with a good way. Oh, well, displacement has the word place in it, like location, like direction. I don't know. I just thought of that right now. Maybe I'll go with that. There are many, many, many more. What are we going to be looking at this unit? Those are the big ones we're going to be looking at this unit. But later on, we'll look at, for example, force, and we'll look at work. The symbol for work is a capital W. The symbol for force is a capital F with a vector symbol over it. In a textbook, they'll write vectors in bold font. In other words, for force, they would bold font. Don't write that down. They would bold font it. That's very cumbersome to handwrite. And so now, especially because with modern software, it's easy to put that vector symbol in a textbook. 60 years ago, it was very difficult to add that arrow. Typewriters didn't have that, but they all had bold font. So now we use, there's a vector, okay? Although since we're lazy, we often just write half the arrow. All right, let's talk about some specific terminology. Distance versus displacement. Distance is how far an object has traveled. What symbol are we going to use? Don't write this next bit down. Isaac Newton used a lowercase f, don't write that down. The British still use that. I don't like it because if I write it really fast, that also looks like the number 5 and it's confusing. And also, what does S have to do with the word distance? It's from Latin. There's some word in Latin that means distance. Many textbooks, especially if you go to post-secondary, they'll use an X for don't write that down, for a horizontal distance and a Y for a vertical distance. And I'll do that sometimes, but I'll introduce that when I need it. I'm going to keep things simple. I'm going to use, write this down, a D for distance. Which, by the way, is terrible teaching. Zena, are you doing calculus this year? Okay. In calculus, a lowercase d means something very specific. And so I'm kind of being a bad teacher using it here, but I figure those of you that will take calculus, you'll be able to keep them straight, and I'm willing to compromise because D. Displacement is an object's change in position. Isaac Newton, don't write this down, used an S with a vector symbol. Some textbooks will use an X with a vector symbol. We're just going to use a letter D with a vector symbol. Write that one down. I need to do a little walk to show you the difference between distance and displacement. So here at the front, I'd like you to imagine that every single step that I'm taking is exactly 1 meter long. That's to the right. We're going to call this positive. This is to the left. We're going to call it, okay. Distance. Count my steps. Count with me. No. Count each step. Count with me. 1, 2, 3, 4. How many steps did I take, everybody? My distance would be considered 4 meters. What's my displacement, my change in position? Not 4 meters, but how could you show a direction? Positive 2. Count with me. 2, 3, 4, 5. What's my distance? 5 meters. What's my displacement? 1 backwards, but what will be a better way to show backwards? A shorter way? Negative. My displacement will be -1. So the difference between distance and displacement, distance just asks, if you're walking, hey, how many steps did you take? Displacement asks, where'd you start? Where'd you end up? That's your displacement, the change in position. Is that okay? I've always found just doing a little dance up there is the easier way to describe it. So, when objects start moving, it's useful to be able to describe an object's location. To describe location, we kind of imagine a number line or a meter stick next to the object. Objects to the right of 0, we can call them positive. If you want to, you can call them east and west, but it's much easier just to say positive and negative, so we're just going to go with that. Objects to the left of 0 have a negative position. So here I have the path of a little bug. It says this: a bug walks along the number line. It starts at A, walks to B. You know what? Let's draw a little arrow pointing from A to B like that. Then it turns around and it walks from B to C. So I'm going to go like that. That's the bug's path. What distance did the bug walk? Well, the symbol for distance is D equals. By the way, can you see why some textbooks might use X equals? Because it almost looks like the X-axis of a graph. And if you did that, I'd figure it out. You don't need to measure. We're going to count. How far from A to B? Plus, how far from B to C? Careful. How far from B to C? 10. In your head, without a calculator, what distance did the bug walk? 14 units? Meters. What's the bug's change in position or its displacement? Well, where did it start? 0. Where did it end up? -6. What's its change in position? You could write 6, don't write this down, meters backwards. But what would be a shorter way in this to write backwards? I'm going to use a negative to show backwards. You can write out the word backwards if you want to. The only thing I would say, Mika, is don't write -6 meters backwards, because I would argue negative backwards is forwards. So don't put both. And I think most of us will choose to go with the shorter one because you're teenagers and you're naturally lazy. Next page. Example 2. Suppose that you run 3 different paths from location A to location B. Path 1, path 2, path 3. Along which path would your distance be different from your displacement? I'll give you a hint. 2 of them. Along which 2 paths will your distance be different from your displacement? Path 1 and path? Yeah, in fact, path 2, your distance and your displacement will have the same magnitude. But path 1 and path 3, your distance will be jump, jump. There's your displacement. Path 3, your distance will be that little wiggle. Displacement will be the straight line. Okay. We can use arrows to represent displacement. A bike is moving along a number line from position 4 meters to position -3 meters. Jump, jump. We often use the word initial for the starting value and final for the ending value, but we're going to abbreviate. What would be a good abbreviation for the word initial? What would be a good abbreviation for the word initial? We're going to use a lowercase I as our abbreviation for initial. What would be a good abbreviation for final? Lowercase f. If you look on your green sheet, you'll see a lot of the equations have subscripts with i's and f's. Those are initials and finals. It's a nice shorthand. We're going to use subscripts quite often because, again, we're lazy and we're going to abbreviate. By the way, if you're wondering where we are on your formula sheet, it's the top of the front page is what we're going to be kind of working our way through the next few days. Okay? So we often use a variable x or d to symbolize an object and subscripts I or f to show initial or final. Example 4 says, draw an arrow showing an object that moves from the -4 position to the +5 position. Okay, there's -4. There's +5. There's my arrow, and I'll even label this initial and final. When I write a lowercase I will always put a little curl on the bottom of it, because that way if you don't see the dot from the very back, you can still tell it's not a 1. That's a 1. That's a lowercase I. So just some things I've done over the years to help you all read my atrocious handwriting a little easier, especially from the back row corner. Hey, what's this object's distance? Be obvious. Mika, what's this object's distance? Starts at -4, ends up at 5. What's its distance? Yeah, I did that just for you. 9? Yeah, sorry. Okay, I'll leave that joke alone now for a while. Yeah, 9 what units, please, Mika? Good. What's this object's displacement? You could write 9, don't write this down, meters to the right or forward. What's a shorter way to write to the right or forwards? There's your direction. Okay. Next page. Example 5 says, draw an arrow showing an object that moves from the 7 to the -2. Okay. Here's 7. Here's -2. There's my arrow. There's initial. There's final. Clody, what's the distance this object has traveled in meters? 9 again. I won't make my dumb joke, but I'm so tempted to. You know what? Let's even write D equals 9 meters, and that way it looks like I even labeled it properly. Clody, what's this object's displacement? The magnitude is still 9 meters, but I want to show to the left. And if you wrote to the left or backwards, I'm okay with that. But what's an easier way to write that? Okay, so what we're going to do is in Physics 11 is we'll usually, at least in this unit, we'll let left be negative, right be positive, we'll let up be positive, and down be negative. We're going to change that eventually. Eventually, we'll start letting positive be, Scott, whatever makes the math easier. Because there's no reason, by the way, why you couldn't let left be positive and right be negative. The physics will still all work just fine as long as you're consistent. And so eventually we'll reach the point where we just say, which makes the math easier? That's positive. But that'll be a couple of units from now. D vector, -9 meters. B says, draw an arrow showing an object that moves from the 7-meter position to the -2. Okay, 7-meter position to the -2-meter position. and then to the 3 meter position. I guess this is initial, and that's final, and there's a little intermediate step. Okay. I can do this. I think I can. What's the object's distance? Well, it made 2 trips. It looks like one trip is 9 meters, and the second trip is how many meters? So distance is, I can do this in my head, 14 meters, yes? Oh, Mr. Duick, that was sloppy. I should not have put a vector symbol on it. Distance is a scalar. Sorry about that. What's this object's displacement? Where did it start? 7. Where did it end up? 3. What's its displacement then? And doesn't care about the path in between. In fact, if it had zigzagged back and forth for an hour, displacement does not care. Distance does. Draw an arrow showing an object that moves from the 4 meter position to the negative 3 meter position, and then back to the 4 meter position. So I guess here's initial and here's final. All right. What's this object's distance? Brennan, what's this object's distance, my friend? Braden, sorry, not Brennan. Braden, I botched that. I apologize. Braden, what's this object's distance? Well, 7 plus... In your homework, if you can just do that in your head and get straight to the answer, go ahead. I'm showing my steps in my notes so that when we're studying later, just in case you forget what the heck we were doing, you can go, oh yeah, that's what we did, right? So I'll usually show more work in the notes than I'll require you to show. In fact, you're going to find I'll try and challenge you to do a lot in your head in your homework. Hey, Braden, what's the displacement? Your hint is it's a bit of a trick question. What? 0. Yes? If you end up back where you started from, your displacement would be, your change in position would be 0. Next page. A ball is thrown straight up into the air. It rises a distance of 11 meters and falls back down, returning to its origin. What distance did it travel? Let's try doing this one in our head without showing any work. What distance did it travel? 11 up and 11 back down. I beg to differ. What distance did it travel? 22. Yes? Jonah, what's its displacement? Why? Because it's ended up back where it started from. All right. There's a little bit of the difference between distance and displacement. Is that okay, Aiden? Okay. What about speed versus velocity? Average speed is, what am I going with here, Mr. Duick? I think I'm going to, you know what? I was cutting and pasting, and I'm going to scribble this out, I think. Now I need to look and see what I wrote on your green sheet, because I don't quite get what I was getting at here. That was a typo, I think. Yes, it is. Good. Okay. Average speed is distance over time. And you can cross out that where triangle equals blah, blah, blah. As an equation, our symbol for speed is a lowercase v without a vector sign. It's v for velocity. Remove the vector. Now it's speed. Look up. Don't write this down. There is a symbol for average. It's a horizontal line. The problem is when I shrink down your type font on your green sheet, it's hard to tell the difference between that and a vector symbol. The photocopier doesn't always photocopy it very well. So I'm going to write as a subscript average or av. I think that's what I did on your green sheet. And it's going to be distance over time. What would the units be? Well, what do I measure distance in? Meters. Over. What do I measure time in? Seconds. You may have picked up by now that I hate memorizing stuff. I'm going to tell you it's absolutely worth memorizing what units go with what topics. And if I ever say something is worth memorizing, because I hate memorizing stuff, if I say it's worth memorizing, it's really worth memorizing. Again, you're not going to need to do flashcards. You will just memorize it because I'll repeat it a bajillion times over the next few weeks. But that's something just to keep your brain open. And okay, if I see meters per second, that's a speed. Scalar or vector? Speed. Scalar or vector? Scalar, you say? Okay. Average velocity. Average velocity is displacement over time. And you might write it like this: delta D over delta T. Where that delta, what is a delta and abbrev for? I think I put it on your green sheet. I think on the first or second row. Did I not? What is that triangle and abbrev for, Maddie? Change in. So average velocity is the change in the displacement, the change in position over time. And I should have put a vector sign here. So as an equation, we say this: average velocity is displacement over time. Now you may notice I stopped writing the change in front of time. Time is always a change in, because anytime you're measuring time, you're starting and stopping a stopwatch. And so, Eric, we get a bit sloppy in physics because time is always a change in. We stop writing the delta in front of it. I think you'll see on the first line on your green sheet, I often put a delta in front of the T, and then Clody, as you look further, you'll see we just stop. What are the units? Also, meters per second. This one is a vector. Average velocity. So, way back in example 1, we did a bug trip. Suppose the bug trip took 30 seconds. What's the bug's average speed? Well, the average speed is going to be the distance over time versus B, the average velocity. The average velocity is going to be the displacement over time. We'll turn back in a second, but Scott, how much time elapsed according to example 6? How many seconds? So let's put a 30 here, and let's put a 30 here. And now I'm going to scroll back to example 1. Oh, there it was. Here's our bug. I guess the distance was 14. The displacement was -6. 14, -6. Now you're probably going to need to get out your calculator. Oh, by the way, look up. 14. How many Sig Figs? 2. 30. How many Sig Figs? I guess technically I should go to 1, but I'm going to give you a little secret. Since we just wrote a test on Sig Figs, let's decide we're going to ignore Sig Figs for the rest of the year. You okay with that? I'm going to ignore them. I'm going to say, you know what? Give your final answer to 3 sig figs when in doubt. That's usually a pretty good level of accuracy. So, 14 divided by 30, I have no idea what this is going to be. 0.467, if I round off properly. Meters per second. It was traveling an average speed a little less than half a meter per second. That's actually a pretty fast-moving bug. Ooh, what's the average velocity? First thing I noticed, you're going to get a negative answer. 6 divided by 30, I can do that one in my head. It's going to be 1 over, is it negative 0.2? I'll even add the extra 0 so it looks like I went to 3 sig figs. Meters per second. What does that negative mean? It means on average that bug was traveling backwards. Not always, but overall that bug was traveling backwards and it must have ended up behind where it started from, which it did. Is that okay? All right. If V average equals D over T, first of all, this little equation here, how many variables does it have in it? How many? 3. A V, a D, and a T. It's actually 3 equations in one. You can memorize all 3 equations, but what I'm going to start to do, starting today, I'm going to teach you how to derive equations in your head so that you don't have to memorize them. I've had a few kids try and memorize their way through Physics 11, and usually about halfway through the course, they just break down and give up. I'm going to be teaching you something called formula manipulation. Zena, was it useful to be able to rewrite equations in your head last year and this year? It saves you, what, about 90% of your memorization, right? So it's going to seem a little weird at first. Some of you will catch on to this right away. Some of you, it will take a few days. As long as you don't quit on me, I've never not been able to teach a kid how to do this, and it is a much better place to go. You may have had some teachers give you like stupid triangles and things like that as dumb. We're going to be well beyond that. We're going to learn how to rewrite anything in our head, Clody. So I want to get an equation for displacement and for time. I'm going to write down what they gave me. I'm going to leave off the average and the vector signs. I'll bring them in at the end because they're just going to clutter things up right now. I want to get the D by itself. What side of the equation is the D on? Left side or right side? Be obvious. So first of all, that means the left side is just going to drop down like a domino. It's going to stay where it is. On the right side, where the D is, what else is there? A T. See it? What's the T doing? Adding, subtracting, multiplying, or dividing? Dividing by T on the right is the same as doing what on the left? I think I heard someone say it, right? Yep. Don't write this down. Look up, look up, look up. Don't write this down, but look up. That equals D, but do you mind? I'm going to put the D equals on this side because that's where we're used to seeing the thing by itself from our math days. Here is another equation. That's a vector. That's a vector. There's my equation for displacement. It's actually the average velocity times time. That will help you calculate a displacement. I think I even gave you that one on your formula sheet, I think. Or did I? Top row or second row, probably top row. I'm seeing a nod. Okay. As we progress, as you get better at this, I'm going to give you fewer and fewer variations of equations. I'm just going to say, Jonah, you can rewrite them in your head. Trust me. So there's yet another equation. Oh, this also wants me to get the T by itself. I would not start with this one because the T is on the bottom and that's yucky. I would start with this one. So, oh, there's my cough finally. Over here, I'm going to write D equals VT. I know it's D vector. I know it's V vector. I know it's average. I'll bring those in back after because it's just going to clutter things up. I want to get the t by itself. What side is the t on? Right side? That means the left side is just going to drop down like a domino. I want to get the t by itself. What else is on the same side as the t? A v. What's the v doing to the t? Adding, subtracting, multiplying, or dividing? So how would I move the v over? Timesing by v on the right is the same as what on the left? That equals t. Oh, wait. Instead of writing equals t, do you mind? I'm going to put t equals on this side because that's where we're used to seeing the thing by itself. I doubt I gave you that one on your green sheet, or did I? I think this would have been the first one where I just said, nah, I'm not going to put it on. I'm going to let you derive it. Okay. And what our approach is going to start to be is, before we plug in any numbers, we're going to rewrite and derive the equations so we can see how everything fits together. Example 7. A motorist travels 350 kilometers during a 6-hour period. What was his average speed in A, kilometers per hour, and B, meters per second? Okay. Ladies and gentlemen, this is our first physics word problem. Word problems in physics are way better than in math. The math ones are stupid. They're really contrived. The physics ones are much clearer. Whenever I see a physics word problem, the first thing I always ask is, what are they asking me to find? And unlike in math, where you're like, hey, what do I let be x? In physics, it's usually going to be pretty obvious what they want me to find. Mallory, what's this question asking me to find? What was his average speed? What symbol are we using for average speed? I'm going to write, so here's what I do. I want to write down, they want me to find the average speed, but there's no way I want to write out that much. So here's what I always do. As soon as I know what they're asking me to find, I go VAV equals question mark. Why? I've written something down. I feel better. The question L is no longer blank. It's not staring at me. I'm not all panicky. I got this. Then what I do is I read through the question looking for numbers and physics words. Now, you haven't learned any physics words yet. Those will be in the next few days. But the first number I see, Mal, is the 350. What are the units next to that 350? What is that 350 then? Time? What is it? I'm going to write D equals 350. Then I see a 6. What's that 6? How do you know? This is why I said it is worth memorizing what units go with what, because by the end of the year, you'll have learned about 40 units, but you'll be able to just glance at a question. Oh, I know exactly what that is. I don't even need to read the question. I saw the number and the units next to it. Really handy. What units, Mallory, does A want me to find the average speed in? What units are next to the 350? What units are next to the 6? This will work. Now, what if they had given me the 6 in seconds or minutes? I would have to do a conversion. Or what if they had given me the 350 in meters or decis or something? I'd have to do a conversion. We won't do very many conversions. We'll do a couple, because I just did a whole unit on it. We'll do a couple of the most common ones, but we're going to develop a shortcut. So, you ready? I would now say to myself, I'm looking for an equation that has a V, a D, and a T in it. You know what? There is one. I think it's going to be D over T. Now, you might say to yourself, Mr. Dewick, this seems like an awful lot of right. Trust me, when we get to more complicated stuff, this is the method we'll fall back on. Mal, what's D? What's T? 6? What do you get? I have no idea. 58.333. I'll go to 3 Sig Figs. 58.3. Units. Since there's a part B, I'll draw a little line. Jada, what does part B want? What does it want the units in? What per what? Loud and proud. You're right. Say it again. Our preferred units for speed in physics are meters per second. However, cars measure it in kilometers per hour. This is going to be the big conversion that we're still going to do all year long. From meters per second to kilometers per hour, or from kilometers per hour to meters per second. What we're going to do right now, we're going to do it once, and then we're going to see if we can come up with a shortcut and add it to our green sheet. So you're going to want your green sheet out. In fact, we're going to add it to the bottom of the front page of our green sheet in just a second. Jada, I guess I want to convert this, yes? Oh, I guess I'll write down what they gave me. 58.3 kilometers per hour. I want to get rid of kilometers. It's going to end up where? On the? Yep. And just meters on the top, and kilo, 10 to the 3. Okay. And I want to get rid of hours. Do you happen to remember how many seconds there are in 1 hour? Good. 1 hour is 3,600. Okay. Here's what I notice. To go from kilometers per hour to meters per second, it's times by 1,000, divide by 3,600. You know what it really is? It's divide by 3.6. That's what that simplifies to. So don't write this down just yet. We're going to add this to our green sheet in as little writing as possible. Don't write this down. Here's what I think. On the bottom of the front page, I would probably write something like this. Don't write it down until I'm done. I would say kilometers per hour. Over here, I would write meters per second. I would draw a little arrow, divide by 3.6. Hey, by the way, to go from meters per second to kilometers per hour, instead of dividing by 3.6, what do you think we do? Write something like that in such a way that you know you have this. And you'll probably end up memorizing this shortcut because we're going to use it so often. But again, the only reason you should memorize something is because you get sick of looking it up. So now we've got a shortcut, a handy way to go from kilometers per hour to meters per second. Mallory, when we're reading our numbers like we did, the 350 and the 6, the other habit we want to always be doing, check the units to make sure they match. Oh, I got hour, I got kilometers and seconds, and they want kilometers per hour. No, I'm going to have to do a conversion. So you've all added that to your green sheet? Good. What is 58.33? Oh, you know what? I'd like to introduce all of you to your answer button. I'm not going to type 58.3. On my calculator, I have 58.3 repeating, which actually is the answer. So all of you have an answer button. For many of you, it's right next to your equal sign, and it may even say ANS. On my TI, it's second function, this. For some of you, if you have a Sharp, it will be alpha equal sign. For the Casio, I think you have an answer button, an ANS button somewhere on yours, Mika, I can't remember. But I'm going to go answer button divided by 3.6. It's more accurate, it's less typing, and there's less chance of you making a typo or an error. It's a triple win. So use your answer button whenever you can, Zaina. It's less writing, it's more accurate, and you won't make a typo. And I get 16.2? Yeah. I like example 8, I like example 8, I like example 8. Example 8 is a nice question. Why would I say that? Did you hear me say it's going to be on the test? You're the kind of student that tends to notice when a teacher emphasizes things? Good. How many of you have ever been somewhere where there's a great echo, a delayed one, where you can yell something and there's a pretty significant delay and then you hear it back? Yes? It's pretty cool, right? I'm still enough of a kid. If I find somewhere where there's a good echo, I'm shouting for a while, right? All right. Speed of sound is 330 meters per second. Sheldon is shouting at the base of a steep mountain. If the mountain is 420 meters away, how long will it take before Sheldon hears this echo? Okay. Sadie, what's this question asking me to find? Sadie. God, geez, I'm botching names. Sophie. I am out of it today. Sophie, what's this question asking me to find? How do you know? How long? Now, how long is a bit tricky. The word how long, the phrase how long in English, can mean time or distance. How long was the movie? Time. How long is the football field? Distance. So you'll have to do a little bit of reading the context of the question, but I agree with you. So let's say it again. What does it want me to find? I'm going to write down. Have I written something down? I feel better. Right? Okay. What's that 330, Sophie? What's that 330, Sophie? What are the units next to it? So even if the word speed hadn't been there, I think I could figure out it's a speed because it's meters per second. Now, there is the word speed there, so I'm going to say, okay, V equals 330. What's that 420? How do you know? Oh, it's meters. What is it in terms of my physics concepts? I think it's a distance. I'm looking for an equation that's got a T, a V, and a D in it. There is one. The one that I gave you on your formula sheet says this, I think. Yes? I'm going from memory here, but I think you have that, or am I wrong? No one's correcting me. I got to look at a formula sheet and find out, Mr. D. I'm going to look at yours again. I have V average equals D. I have D equals V average T. So I should have put the AV in. Well, the average here will be the speed of sound because the speed of sound doesn't speed up or slow down, so it is its own average. Sophie, I want to get the T by itself. How? Yes. T is going to be D divided by V. What do you get? Well, it's going to be 420 divided by 330. By the way, the speed of sound varies. It depends on temperature and humidity and altitude and a bunch of stuff. So it can be anywhere from about 330 to about 345, depending on various circumstances. And that's through air. It's different through different objects. That's why underwater things sound different, because the speed of sound through water is different than the speed of sound through air. You get 1.2727272727. Yes? Why is that wrong? For a candy, can anybody tell me why this must be the wrong answer? I'll give you a hint. Echo, 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 echo. Anybody see it? Why can't that be how long it would take you to hear the echo? Yeah. Mika, Candy, what? Why? It goes there and really I should have either doubled this distance because it's going there and back, or I can double the time afterwards. So I'm going to double the time afterwards times 2, and you can make a little note there and back. I'm going to use my answer button times 2. and I get 2.5. 2.5 what? Is that 4 going to stay a 4 or become a 5? By the way, the flip side of this, if, Claudia, you're ever at a neat place where there's an echo, time how long it takes for you to hear it, and you can figure out how far away the cliff that you're bouncing your echo off is. It's going to be 330 times the time. Oh, but that's twice the time. You have to divide the time by 2. Kind of cool. Okay? I've been talking for a while. I'm going to pause here. I'll pick up with the tail end of this next class, but for now, so next class we're also going to be doing a short lab in the second half of class. You can certainly start number 1. You can start number 2. 3 is good. 4 is good. 5 is good. I'm eventually going to assign all of these questions. If you feel like trying it yourself and working ahead for a head start, you can. But with the remaining little bit of time that we have here, you can work on those. Okay?